So, I believe this is where we left off yesterday. Or are we?
Wait, yeah, you're right.
Ah, that's it. Yep. Okay. So, what we went over yesterday was our horizontal translation. And we defined a horizontal translation, our movement left and right, with the notation of f of x minus h. Vertical translation was our f of x plus k. Then we went over reflections. Across the x-axis, we use negative f of x. And if it was across the y-axis, it was f of negative x. And these are the ones that we had and went over yesterday. We were partway through reflections, and we went through our horizontal and vertical already. Questions on this so far? So we'll finish up reflections and look at the last part, which is our horizontal and vertical stretch and shrink. So if we want to write a function g, whose graph is a reflection of the y-axis of the original function, well, across the y-axis is our, guys, f of negative x. Because negative f of x would be across the x. F of negative x is across the y. And again, as we looked at these yesterday, since we don't have f of x anymore, we have f of negative x, which means that we have to change every x in our function from x to negative x. So for our g of x function is going to equal, we'll have the absolute value. We replace the x with negative x. Then we have minus 5. The other absolute value minus 4. Now we can drop the absolute values or simplify those out, giving us this here. Now if there had been a number in front of the parentheses, we'd have to multiply it and the negative x together. But since there's not one, we just have this here. Any questions on any of this here so far? We ready for the next one? Now again, just like with the previous type here, when we got to this one, it doesn't give us a name or tell us what we need to name the new one, so we'll just call it g of x. But we want to take this function and have it reflected in the x-axis. So if we're doing a reflection in the x-axis, we're going to start off by saying g of x is equal to negative f of x. Because according to our definition, a reflection across the x-axis is our negative f of x. Thank you. Now, since we didn't do anything to the x inside the parentheses for f of x, it's still just f of x, we can just rewrite the function in. So that means we'll have our parentheses negative absolute value of x plus 2 minus 1. Then what do we do next? We need to distribute the negative to both terms. Now again, like we said yesterday, that negative will not go inside the absolute values, but it will multiply out front. So our negative times our negative would be a positive. So we just have the positive absolute value of x plus 2, or we just say absolute value of x plus 2. And our negative times negative 1 would be plus 1. And that's it. We're ready to look at the last one with reflection. Now this one here, we want to reflect this function in the y-axis. Now again, I'm going to call it g of x. And this would indeed have a vertical shrink of the original function, parent function. Since we're talking about the y-axis, we have f of negative x. Now this time, unlike the one we just did previously, we have to replace every x with negative x. So we'd have 1/2 parentheses negative x plus 1. But yes, if I just do this one step at a time, but if we do, because we will, in this case, have to multiply the 1/2 and negative x together to simplify those parentheses, which would indeed give us negative 1/2 x plus 1. Have one? They should. Any questions on these here with reflections? The next thing we're looking at is vertical stretch and shrink. And this time, we actually also have horizontal stretch and shrink. Now again, just like with our previous types of transformations, we do have our setups with this here. For horizontal, we do have horizontal stretch, shrink. I will talk about it second, but it is our f of ax. And we also have vertical stretch, shrink, which is our a times f of x, where a is the amount that we are stretching or shrinking the function by. So with vertical stretch and shrink, when it tells us that the function is going to have a vertical stretch at 2, we replace a with 2 and then simplify the function, kind of like what we did with the reflection across the x-axis. If it's a shrink, we replace a with whatever that shrink is and multiply it through, kind of like what we did with the reflection across the x-axis. Horizontal stretch and shrink. We said anything inside the absolute, inside parentheses or absolute values is the opposite of what we think, yes? Yeah. Now, if we look at the definition, the graph of y equals f times a of x is a horizontal stretch or shrink by a factor of 1 over a. Not just a, 1 over a. Of the graph y equals f of x where a is greater than 0 and not equal to 1. If it's between 0 and 1, so the graph stretches, so here the function stretches the graph horizontally away from the y-axis when a is between 0 and 1. It's the opposite of what we think. So if it tells us that we have a horizontal shrink or a horizontal stretch, we have to flip it. Flip it before we plug it in. So if they tell us that the horizontal stretch or shrink, one of them, is tell us that that value is 2, we don't plug 2 in. We plug in 1 over 2. We have to flip it. If it tells us the horizontal stretch or shrink amount is 1/2, we have to flip it. Opposite of what we think, we've got to flip it. Because if it looks like a stretch, we're talking horizontal, it's actually a shrink. If it looks like it's a shrink with horizontal, it's actually a stretch. And years past, have not covered this because, again, just that complexity to it. But it's really whatever the value that we have for horizontal stretch or shrink has to be flipped. Then we just plug it in. But vertical is actually exactly as it looks like. So the first one we'll look at is actually vertical stretch. Vertical stretch. Let f of x be this here. Write a function h of x, whose graph is a vertical stretch of the graph of f by a factor of 2. So we're talking about vertical stretch or shrink. Our main setup is a times the function f of x. A times f of x. And what are we stretching the graph by? 2. So that means our value of a is, we have 2 times the function f of x. Blushing. Now, since we still just have f of x, we haven't changed what's inside the parentheses. We can just replace f of x with its function. The value of x minus 3 minus 5. Question so far? Anything that's not clear? Hopefully this seems very similar to what we did for reflections across the x-axis, except instead of having a negative sign, we have a 2. We'll do the exact same thing next. We're going to distribute this 2. And just like with the negative, the 2 will not go inside the absolute value, so it's just going to go out front. So we'll have 2 times the absolute value of x minus 3. And 2 times negative 5 is? And that's a vertical stretch of 2. Questions on this here? We ready for the next one? Before we move on to the next one, any questions? Not so far? Maybe later? This one here, write a function g whose graph is a horizontal shrink of the graph by a factor of 1/3. So, since we're talking about horizontal is the opposite of what we think. Or horizontal. Okay. With this here? Yeah, I need to fix that. I said that last year, I think, too. We're going back to horizontal. Because when I originally set these notes up, I was doing just pure vertical. But I believe y'all can actually do these, especially with horizontal. I need to fix the note sheets. Again, because there's one key step that all we have to do. Flip 1/3. And if I flip 1/3, what do we get? 3. Because it's, I mean, if we technically looked at it, it'd be 3 over 1, but 3 divided by 1 is just. And that's it. Now we just use the methods that we've been using up to this point. Because if we're writing g of x as a horizontal shrink, we're using f of a times x. F of a times x. Now what is the value of a? It would be 3. F of 3x. So whenever we see horizontal, we just have to flip that fraction, whatever it is. If it had been 2/3, we would have plugged it in as 3/2. Or if it had started out as 3, we'd plug it in as 1/3. Now, just like with our reflection across the y-axis or our horizontal translation left and right, we don't have f of x anymore. We have f of 3x, which means every x in our original function has to be replaced with 3x. So we'll still have the absolute value bar. 3x minus 3 minus 5. And we can simplify a little bit, which just really means removing the parentheses. So we get this here. So the real big trick with horizontal is not so much the plugging in or how it's using. It's just making sure to flip the factor. Vertical, outside parentheses, exactly as we see it. Inside the parentheses is opposite. We don't have to do a whole lot with our horizontal translation left and right, as long as you remember the correct sign, with left being negative, right is positive, plugging those in correctly. There, this, we just have to flip it. Questions on this here? Let's look at the next one. And again, I change it. I'm definitely going to need to go back and change the note sheets. One over 5. Because we're talking horizontal stretch. So the actual number we plug in is 1/5. So, okay, g of x is equal to f of a times x. F of a times x. Because that is the one we use for horizontal stretch and shrink. Now the value of a is 1/5. So we have 1/5 x. Now again, just like with the previous one, all we need to do is plug in that 1/5 x, and for every x in f of x, minus a g of x is equal to absolute value of 1/5 x minus 1 plus 2. Scroll up just a little bit for y'all. Now, since there's not a number in front of the x, we can just drop the parentheses, and we get this here. Any questions on any of this so far? Are you ready for the next one? We good with all this here? Yes. Write a function h whose graph is a vertical shrink of the graph of f by a factor of 0.25. So since it's vertical, it's exactly as we see it. And we're using a times f of x. Now the value of a is our 0.25. So we can replace a with it. That's fine too. Now we can replace the f of x with its function, which is the absolute value of x 1 plus 2. And again, just like the previous one, we can distribute the 0.25 and simplify. So our 0.25 times our absolute value is just going to be 0.25 times the absolute value of x minus 1. Plus, we need to do 0.25 times 2 would be 0.5. Yeah. If we wrote it as fractions, h of x would equal 1/4 times the absolute value of x minus 1 plus 1/2. Either will work. If you convert one of the decimals to a fraction, I would prefer you do all of them as fractions. Either write them all as fractions, as long as they're not whole numbers or integers, or leave them all as decimals. Questions on any of this here? How do we feel about vertical stretch and shrink? Feel good with this here for the most part? I know I'm skipping two, but I want to look at these last few here, because these also have our vertical stretch and shrink with them. Combining translations is the last part we're covering in 1.3. Now, combining translations seems like it's going to be a harder thing than what we've done, but all we're doing it is one step at a time. The biggest thing I will say when we do more than one translation is just take them one step at a time in the order in which they're listed. So if we look at this here, let G be a vertical shrink by a factor of 0.25, followed by a translation 3 units up of the graph f of x equals x. So, which one was listed first? Vertical shrink of 0.25. So the first thing I'm going to do is do that one. Now, I'm going to call it something other than g, because g of x is the final one, our final answer. So I'm going to call this h of x. And the way that we name this isn't really important. I'm just giving it another name to do this middle step. So vertical shrink of 0.25. Well, vertical shrink is our a times f of x. Well, what is our value of a? .25 or 1/4. We're going to do this one first. Now we can replace f of x with its function, and its function is x. I could put parentheses around it, but it's just going to become 0.25 times x, yes? Any question on how we apply the vertical shrink? What did it tell us to do next? 3 units up. And we want to call the final function g of x. I'm not going to be a nitpick on how we name it, g of x, h of x, z of x. I'm mainly looking at the function itself. Because again, f of x, g of x, all of these are just ways to name the function specifically, yes? So the ones that we've been using up to this point, just using f of x has just been a way to name it. And it's just standard form to just use f as the original function. Don't know why. It's just how they normally do it. So here, our vertical is normally we say f of x plus k. But what are we affecting or changing now? We're changing the function h of x, yes? So really we're saying g of x is equal to h of x plus And up to this point, we've been using f of x for all these because the original function we started with was f of x. So we're good with that change. So it's just another function. This is the function we're talking about. We're still not talking about f of x that we're affecting anymore. We're talking about h of x, our 0.25. Now, what is our value of k? Because it said 3 units up, yes? So the k value is 3. Would it be positive or negative? Positive. Now we just need to plug in h of x, which is that's simplified as it gets. So this first one started out very nice. We didn't have any kind of real crossover. But really with combinations, we're doing exactly what we've been doing today and yesterday, just one step at a time. Questions on this here? Let the graph of G be a translation 6 units down, followed by a reflection in the x-axis of the graph f of x equals the absolute value of x. Start off with calling it h of x. So we're talking about going down. Up and down is vertical. So we're saying f of x plus k. What is our value of k? Vertical stays how it is. Horizontal is the opposite of what we think. And luckily for plugging it in, if it is left 6, we can plug in h as -6. Because again, inside vertical is x minus h. So if it was x minus -6, the negative and negative would make a plus, make it positive, which would do the change for us. The only one we have to actually do on our own is horizontal stretch or shrink. That's the only one we have to manually change. The rest of them will change just by the function notation. Well, what is f of x? And up to this point, we could have done both of these together, done them at once, but I've just kind of been doing step by step. Now we could simplify this a little bit and just say h of x is equal to the absolute value of x minus 6. We don't have to leave it as plus and negative. And we get this here. Reflected across the x-axis for our g of x. And across the x-axis is our negative. Normally f of x, we'll call it h of x. And again, that's just notation, just how we write it. In that we're not talking about f of x, because f of x is just our absolute value of x. We want to talk about the function that had the horizontal, or vertical translation of 6 down. And we want to talk about the absolute value of x minus 6. That's the function we're applying this to now. Y'all kind of see how the difference between those two. I would not get as fixated, because these are very helpful that we have these notations, but I'm just changing it from f to h to say that we're talking about this function now, not this one up here. That's all it's doing. Now, at this point, we can plug in h of x, which is our absolute value of x minus 6. And we can distribute the negative. Again, the negative cannot go inside those absolute values. So we'd have negative absolute value of x plus 6. That'd be our final answer. Questions on any of these here? Was the combination of translations as intricate as you thought it was going to be?
It's just I remember
Huh? Yes. Because the absolute value of negative x is going to be different than the negative absolute value of x. Because inside we're talking about y, outside we're talking about x. Now, one thing that is interesting is if x is by itself inside absolute values, or we had it negative x by itself inside parentheses squared, this is actually the exact same thing as saying this, and this is the same as saying x squared. For the most part, yes. One of the properties of absolute values is that the absolute value of a times b is equal to the absolute value of a times the absolute value of b. We can split the two numbers apart if we just have one term, which means here, erase this, I can really say this is the same as negative 1 times x. We good with that step, yes? Now, by this definition, I can split these two terms up, saying it's the absolute value of negative 1 times the absolute value of x. Well, what is the absolute value of negative 1? Positive 1. 1 times the absolute value of x, which is just, if you want to leave it, stop erasing. This is just the absolute value of x. If you do get one of these on the homework, I am going to take it as the absolute value of x. I'm not going to mark it wrong that you didn't change it from the absolute value of negative x to just the absolute value of x. These are both the same thing, okay? If it does come up on the homework, most likely the book is going to write it, if you check the answers on, if it's an odd one, as the absolute value of x. I will take either. They're both the same thing, okay? I believe that is it. So homework on page 22, 3 through 6, all, 11 through 14, all, 17 through 20, 27, and 29.